And it has been found that if you damage your prefrontal cortex, then you will talk without thinking. You make perfectly good sentences, but it is inappropriate, it's not what you want to say, but that is because it is your prefrontal cortex that controls the Broca's area, and it inhibits it and makes it not say things that you don't mean or that are erroneous. So what it means is that we cannot just keep training these LLMs, larger and larger LLMs, because they are really statistical machines, just based on the word occurrences. So if we learn from this from our own brain, we know that we need to have external control. And this is why we're working on this language. It's called GenieScript. GenieScript is kind of like the prefrontal cortex in a sense, because it controls how the LLM works. It sends in the input, and whatever LLMs put out, it filters it, and maybe it sends it through the large language models multiple times before you deliver the message to the end users. So it's like talk with thinking rather than talk without thinking. And we talked about the fact that the LLMs hallucinate, it doesn't have the real facts in it. So what we do also is to add truthfulness so that you can trust this agent. And the way we do that is that we actually fine-tune them so that we generate the code so we can consult external knowledge databases. For example, if you ask me some questions I'm not so sure of, I will go and consult with the trustworthy databases. We need the LLMs to do the same thing. So we fine-tune it so that the language, the natural language is translated directly into code. I can call APIs, or I can go to databases and databases that we trust, and we take the result, you go back to the program, and then the program decides what to say. Okay, so this is providing control over the statistical natural language processing center. So that's the basic idea. That's what I'm going to talk to you about today. So before we go there, let's talk a little bit about where we are today. There is a lot of research on semantic parsing, which is what we were talking about, just natural language to code. But the commercial systems are mostly commercial conversational systems are mostly built using dialogue trees, okay? And I think of it as assembly programming. So, for example, with dialogue trees, the basic technology is just intent classification. So, if you take something like money transfer, okay? So, say I'd like to transfer $100. The intent classification will set it to the fact that your intent is to transfer money. And when you transfer money, you need to have a from and a to and an amount and so forth. Those are the slots. And you need to fill up the values. Okay, so that's the basic technology that is used by pretty much all of the conversational agents out there. And dialogue tree requires the developers to lay out how the conversation goes. I say, oh, hello, how can I help you? And then the agents, and then the user is supposed to speak, and then the agent, the developer kind of scripts the kind of things that people will say. So, for example, you say, oh, you're looking for a restaurant, and then the agent will say, what kind of restaurant? And if the user says, oh, this restaurant, that restaurant. But if the user says something totally different, like, can you recommend something? The system goes off script, and it's game over. Okay, it cannot handle things that it didn't anticipate. So dialogue trees make very brittle agents. There are three big problems with it. The first one is representation. Okay, intents and slots are just not expressive enough. If I say something like, I'd like the latest train leaving that will arrive by 9:15 a.m. Okay, so that's a very natural language, that natural sentence, but I cannot represent that with a bunch of intents and slots. The other problem is that too many parts. I have to lay out what the agent says and what the user says, and it just goes on and on. Okay, but the user can say whatever they really want. So how do you handle that? And as a matter of fact, you just cannot anticipate everything. Here's an example. Suppose I say, I want to transfer money. And then the agent says, okay, wonderful. How much money would you like to transfer? And then you say, oh my, it's like, how much money do I have in the bank, right? So you say, when you say that, the agent didn't expect you to ask a question when the agent is asking you a question, and now all bets are off, okay? So what I'm going to tell you is based on this very simple principle that says that if you really want a robust conversational agent, it needs to understand every sentence that is relevant to the domain. Okay? It doesn't matter what the agent says. The user can still say whatever they want. And therefore, you just have to understand every sentence about banking, if you're into banking, and restaurants, if you're talking about restaurants, and so forth. Our approach is that we're going to do something very different. Instead of figuring out what the agent says and what the user may say, we say that we're going to train one semantic parser that can understand it all right? It doesn't matter what the agent says. I understand every relevant sentence. And if you do that, then you take that semantic parser and it can be used for any agent in the domain. Okay, you don't have to train a new semantic parser for a new agent. But you say, oh my goodness, okay, you're talking about training as a neural network, but we know that training data are very expensive to acquire, especially when it is conversational. So typically we would say, look, if you want to build an agent for banking, you have to hand annotate tons of banking conversations, one domain at a time. And in order to do that, you have to have real users, because otherwise you don't know what they're going to say, and it is very expensive, it is error prone, and it actually doesn't work very well except for the head, for the most common utterances. And it's very expensive. You look at Alexa, they're very proud, they have 10,000 developers, but today Alexa is still single command, single sentence by sentence commands. But if you want to go to conversation, a common thing to do is to have Wizard of Oz conversations. You hire two humans, an agent, and pretending they're an agent and a user, and they talk, and you capture the conversation, and you hand annotate them. So one of the most popular data set is multi-WOZ. It's a multi-domain conversational data set, and it is still full of errors after 4 rounds of annotations. So what is the solution to this technical problem is that we're going to build this semantic parser with mainly synthesized data. And it is from a domain specification. You tell me what the domain is, and I will build that semantic parser for you using mostly synthesized data. You will have a few, you need to add in some few shot real data, but for the most part, it is mainly synthesized data. And then the last bit is that there are various papers on agents that AI researchers would write. But what we really need is to reach the developers. Remember what I said at the very beginning? There will be many, many, many more agents that do all kinds of things. Today there are over 20 million web developers. I want the same in the future. There will be 20 million developers writing agents that use voice. So you really have to bring it to the masses. And this is the reason why we came up with this new language called GenieScript. It is to let the developers write these agents using the semantic parsers in just a few lines of code without knowing anything about AI. Okay, and that is the way for us to scale to this vision of socially intelligent agents by 2030. So let's get into the details. Let's start with the basic concept is like, what do you mean by it is highly, it is a easier programming language? I will show you how to build a robust assistant in just a few lines. And then we get into the training, which is really where the core of the problem is. And then with this technology, we have built various prototypes of assistants, and I will go over them as well. So, just to remind everybody, we talked about 3 problems in dialogue trees: representation, too many parts, and user interrupts. Let's see how GenieScript solves these problems. So, first of all, the representation, what we use is ThinkTalk. It's a language that we created ourselves. And it's a high-level language for writing the meanings of sentences for virtual assistants. And I'm going to talk about queries, but it actually applies to API calls, and it also controls constructs, like if this, then that, and so forth. Any query can be represented in ThinkTalk, because ThinkTalk is kind of like SQL. Okay? So if you say, I'd like the latest train leaving, and so forth, I can actually write it down. What I'm going to do is that I'm going to do a sort. I figured out when they leave. I sort it in descending order, and you pick the first one that arrives by 9:15. So that natural language is now code, and that's what we need the semantic parser to do for us. So that's a representation. So the second part is that, what do we mean by a few lines? What does I said a few lines, so I should be able to show you the program, right? On one slide. So what do people do is that the developers will provide information about the domain. It turns out that it's just the database schemas, the API signatures, with a few annotations, if you will, if you like, and a high-level agent policy. You don't have to figure out what the agent says and what the user says turn by turn. GenieScript will automatically understand all the utterances in the domain, and as a matter of fact, because we translate it into code, we execute it, and I will give you the answer. You don't even have to interpret that logical representation to figure out what that answer is. Let's see it. So we say that you have to describe the domain. So we built a restaurant assistant, and we're using we're using Yelp, which is very popular in North America. And so you describe what you can do. So for example, if I'm doing restaurants, I will have to have a restaurant knowledge base. And you define the schemas, like I have these fields, and you have strong types. And then you say, and then of course, after you find a restaurant, you want to make a reservation. So that's the API for that, and so you describe the API and the signature, which is that if you want to book something, you have to have the date and time and so forth. And all this is strongly typed, and with this knowledge, we will build a semantic parser for you. And then you get to control what the agent does. It's not pure neural. And I said it is a small number of lines of code. You can actually build an agent with those 1, 2, 3, 4 lines of code. It says hello, I import my database, I say hello, and that is it, because GenieScript will do the rest. So here is an example of many possible combinations of many possible dialogues, this exponential many paths. So you wrote the code, hello, I'm Genie, your assistant, that's the blue line that you write. All the red lines of the agent are automatically generated. On the left-hand side is what the user is saying. You say, I like a French restaurant. I recommend this restaurant. How far is it? The distance is this. Can you recommend and you recommend something nearby? The distance, please book it. Okay, which day? Is it expensive? And you can talk. The user is free to talk about anything they want with respect to the restaurants. And the way we do this is that we translate this natural language into code, and that's in ThinkTalk. And well, let's zoom in. So here's an example. If you say, I'd like a French restaurant, it's a SQL call that says restaurant, cuisine equals to French, very obvious. And then after the recommendation, the user says, how far is it from here? You notice the co-reference, that it is referring to the restaurant, and that is translated into that ThinkTalk that says, oh, find the location, find the distance of that query, and the answer is automatically computed, and then we just write you the answer. And then it says, can you recommend something nearby, and so forth. What you see here is that every turn is a query. And that the dialogue accumulates its meaning. It gets longer and longer as it goes. And this is what we need to do. So the semantic parser is contextual. The total meaning is captured as the input into the semantic parser to interpret the next sentence. So that's how we manage that. And once you are using a representation so strong and it is executable, the exponential paths kind of disappear, because all you have is a simple loop that says, here's the query, I execute, I report. I don't know what you are saying. I don't have to script what you are saying. It just keeps doing it. And if you don't have enough parameters, I will ask you for the slots. And that is the basic mechanism. And if it is action, because we worry about side effects, we do the confirmation. Once you get the confirmation, we execute, we report. So this is the main loop, and it will handle the conversations that I just showed you, which will be quite difficult to script, and it just goes on. You know, it can handle all kinds of paths, dialogue paths. So I said, what do you mean? You just write one line, you have no control. Now I'm going to tell you how to let the developer control the flow, okay? Because what I showed you earlier, everything is done automatically by Genie script. So it is very important, because we said that the agent is going to get a lot smarter with being a companion to seniors and so forth. Okay, it is not automatic. Only the execution of commands are automatic. So we need to have the developer be able to write code. And Genie script is actually JavaScript plus a dialogue library. So anything you can code in JavaScript, you can do that here. So for example, the agent may want to suggest to the user. So the agent may be personalized and understands that the user hasn't been to a pizza restaurant for a while. So the agent would say, are you interested in some pizzas today? So that is the API call that we support, is that you can propose. And besides the English, I'm asking the developer also to talk about the query that goes with it. Because when the user accepts it, we're going to execute that query. Okay? So there is a formal representation to go with the natural language. So the Genie script handles all the dialogue behind the scene, and it returns the result of the query as if there is no need for anybody to worry about natural language. Okay? So here is a full program that says, oh, I check and I notice that you haven't had pizzas, so I suggest that you get pizzas. And if it is successful, I have found a restaurant. It may not be a pizza restaurant at that point. I will propose to make a reservation. Would you like me to book that particular thing? So I'm not letting the user drive everything. The agent is now being able to have control over the conversation. So here is an example of a conversation. This is a happy path. You say, are you interested in some pizzas today? Sure, okay, wonderful. I recommend this restaurant. Sounds good. Would you like to book? Okay, which day? A particular day, can you confirm? Yes. Okay, this is the happy path. This is what people normally code in a dialogue tree, all right? But things don't usually go that way, right? So, just like before, I suggest you pizzas, and I say, I want French. Doesn't matter, because Genie script understands what you're saying. It just continues. And then, would you like to book, and so forth. I want to point out this example here. Would you like me to book? And I say, oh my goodness, how much do I have to pay, right? Is it expensive? And because we understand what it is saying, it doesn't matter what the agent is asking. I know you are looking for the price. I would say it's moderate. The user accepts it, and Genie script automatically goes back and re-asks this question. So you wrote 2 lines of code, the rest are filled in for you. And this is what you mean by an understand it all semantic parser. So as I showed you, this is how we handle the third problem in dialogue trees, and this is being able to handle user interrupts. So I hope I give you a flavor. I mean, it's too short to explain the full language, but that's the flavor of the language. There's a lot there's a system working for you once you highlight, once you decide on the high-level policy. So the second part is this training for semantic parser. with mostly synthesized data. That sounds really hard, right? But I want to draw an analogy. Today, every company has databases. Okay? All they do is that they create the schema and stuff this database with data, and it can answer all kinds of questions. Companies do not write their own databases. There was one single a couple of database software that everybody is using. Why is that possible? Is because it is well known that the database has only about 6 basic primitives, but there are many, many combinations to create all kinds of that match with these combinations you can answer all the queries you can possibly ask of the database. In the same way, we're going to say that I'm going to build you a synthesizer that works for all the databases. Just like the database software itself, I understand the primitives, and I understand the combinations, and I will synthesize data based on that database schema to generate enough training data to create the semantic parser. Okay? It does not matter what the agent is saying. This is what all the things that the user can possibly say. So, to summarize, you get one database software, one database synthesizer. All right? And once it is based on the schema, that means that once I create like a finance semantic parser, then all kinds of companies can be using that semantic parser. Well, more importantly is that you can change the agent policy anytime you want without redoing the semantic parser. So how does this work? It does it in 2 steps. The first is that I want to cover the queries with, to make sure that we have a good sample of the queries that can be made using natural language. Okay, so we stare at the database operators, and then I create templates that generate examples for that, for those operators. And then we compose them, and then we will get the combinations. But these database templates, these templates we made are not just about covering the possible queries. We also want to make sure we have a lot of coverage on natural language variations. So for example, if you give me an attribute, I want to know how this attribute can be described using different parts of speech, okay? And because of typing, the minute that you tell me that it has a time, I can talk about before 9:15 or if it's a location, how far is it? We generate all these questions based on the type information. And we also have all the combinations. And then if you look at this and you say, man, there's something wrong. Natural language cannot be easily described with templates, even though I have about 1,000 of them. Because domain by domain, they have their specific terminology. Okay, this is domain-independent. These are domain-independent templates. So what do? We add the second step. The second step is to leverage the LLMs. The LLMs have been trained on all kinds of domains. So we take the language, the sentences, and we use the LLMs to paraphrase them into more natural English or natural language. Okay, and it is actually a little bit tricky, because you cannot just use the LLMs as the typical paraphrasers, because they do make mistakes. And when you make mistakes and you feed them back in as training data, you will pollute your system. So we actually do some self-training to make sure that the data we have are decent. But I didn't cover conversations yet, so let me do that. Today's state of the art is that you take these Wizard of Oz conversations and you model the conversation as dialogue, as state machines. All right? It's like you start with greeting, you ask for something, I ask you for a slot, and then you answer it, and so forth. There's a little state machine, usually about 20-ish dialogue states. And after you model that, you synthesize examples of the, you synthesize the conversations based on the state machine, and then you paraphrase. My group has always been doing automatic paraphrasing. I don't have the money, and I don't think that they do necessarily that much better, because they also make a lot of mistakes. So we do LLM paraphrasing, as we discussed. And then you take the data, you train a neural network. You always throw in a few shot, by the way. And what that means is that every time you change the agent in the flow, you will have to retrain a neural network. Okay? And this is not doable. Can you imagine writing a big JavaScript program, and every line you change, you have to go and figure out how to generate, have to synthesize data all over again. Okay? So our approach is, as I said, is that we're going to do it all, once and for all. And the basic idea is that we're going to synthesize all the data, starting from the database operations. Okay? But before I do that, let me show you, I want to mention that, you may have heard of dialogue states, which is that you take your conversation so far. So for example, I'm asking for a French restaurant. And then the user says, what is its address? It's incomplete. So a typical approach is that you will have a neurocontextual semantic parser that takes the context and the sentence, and it generates the dialogue state. And in this case, because I asked for French, I'm looking for a restaurant address, that means that you must be looking for the address of a French restaurant. That summarizes the dialogue, and that's called the dialogue state. So this is what people usually do. So what we said is that, let us simplify the problem. We're going to introduce this thing called a sentence state. What is its address? First of all, we say it's a address of a restaurant. We will then, and that is basically what you said. You didn't say anything about French, but I need to figure out what you're referring to, and that's why we pull out the fact that you are talking about a restaurant. And then we use an algorithmic apply operator to generate you the full dialogue state. So this is it's very important to have the right representation. And so this is the way for us to simplify the neural network, the work of the neural network, and more importantly, the work of the annotators and the synthesizers. So the sentence state is the smallest complete think-talk statement that includes all the information in the new utterance, and then the dialogue state is what the new sentence is, plus whatever that you want to carry over. So for example, if I say, originally I asked for French food, and then later on I say, how about Spanish food? Or how about Spanish? Then you do not want to inherit the fact that you wanted French. So there is a conflict. So we can only carry over things that do not conflict. So with this representation, we wrote a bunch of templates. We want to cover all the coreferences, all the ellipses. Those are the two major issues in conversational sentences. Okay? So we basically just say, make sure that everything that you can possibly do with ellipses and coreferences have been covered using these templates. And this is how we synthesize the conversations. And then we take the results and we fine-tune it, and we're using BART. The experiments I'm going to show you are just using BART, and we're in the process of also experimenting with the larger language models. And one thing I want to tell people here who are working on NLP is that if you do anything with NLP, you have to validate it with real-life data. If you synthesize data or automatically paraphrase data, automatically translate data, if you use that data, you get 90-some% all the time. Okay, you have to use real-life data. So that's all the time I have for the technical details. So I'm just going to talk about what we have been able to do with this technology. We've been building this technology for a while. The Genie script is the newer part. Some of this doesn't actually need all the technology, needs Genie script. So I'm going to talk about I'm going to talk about 7 different results that we have obtained. The first experiment we did was on question answering, just straight line, one sentence question answering. Of course, this is something that Alexa, Siri, Google Assistant do all the time. But what we are going after is the long tail. I don't believe that the whole point is to be able to answer questions that everybody asks, okay? That's cheating, all right? Natural language means I have to, if I understand you, it doesn't matter whether it is frequent or not, I understand the language. And what we do is that we look at the database and we come up with all the possible combinations and sample them. I don't know if people will ask them, why do I care? I mean, I'm just going to handle all the database queries. Okay, this understand it all is the principle behind what we do. So as you see here is that for something even like restaurant questions, these are questions that we ask the users for. Okay, this is not synthesized. But the difference, however, is that we show them the properties and we tell them to use at least 2 of these properties. And so these are the longer tail questions, and we actually do better than the commercial assistants, even though we have hardly any manpower. Okay, you have to remember that. And I just show you some examples of the kinds of sentences that we can handle that different assistants may not be able to. So that's the first experiment. And the second one is on multi-voice. As I mentioned, it is the most commonly studied data set, re-annotated 4 times. What we did is to say, I'm not going to count on the hand annotations. I synthesized most of the data. I throw in a few shot, about 2% of what people use in food training. And we got the best turn-by-turn accuracy. We reach about 80%. So this gives us a lot of faith in synthesizing for conversations. We also think that it is very important that we reach everybody. You know, I said it is going to change the world, and the world doesn't just speak English or a few major languages. There are many, many languages being spoken in the world, and we want them all. So the first step is that we want to do everything that we have machine translation for. If you look at the open source Marian project, it has 555 languages in there already. Okay. And so the idea here is that if I have the data set for, say, English, can I translate them to all, many different languages? So here are some of the languages that we have tried. But if you try this straight up with a machine translator, it doesn't work very well. You have to be very careful about the entities, okay? Because the entity names in one language, when they translate to another one, it's screwed up. And when you go to a new language, you really have to talk about the new language entities. So we're very careful with the alignment on entities. And if you do that, you can actually improve the performance. We were at about 70-ish% in English. As you see here with Genie, we are closer to that, even though all we did was to use 2% of manual annotations. Okay, and that's why we say you can do go translate it to different languages in one day, because you do need a little bit of manual labor, but not a lot. So, so this was reported in the that's the EMNLP paper, and recently we started doing more work on multilingual dialogue systems. So besides multi-voice, the group from Tianjin has been working on this data set called Reason-voice, which is even bigger and it is much better annotated. But it's in Chinese, and we really want to get it to many, many more languages. And so the approach that we always take is to minimize the manual work. So we focus on automatic translation, and we only use human post-editing for the few-shot data, the validation data, and the test data. Okay, you always validate and test on real data. So we partnered with the Reason-voice makers, they are Tianjin, and they have Chinese to begin with, and they are the ones who actually translate to English, because not too many people in my group can understand Chinese. So, and then we reached out. We've got French from the CEA group. We have German from Hasso-Plattner Institute. We have Hindi from IIT Hyderabad. And we have mixed code, Hindi-English, from Microsoft, India. And also Korean with Hanyang University. What is missing here? Spanish! What happened? Well, this is why I'm here. I think that it is an example of something that we really want to have it spread. Okay, by creating this data set, it allows everybody to be doing work with a very good data set. And we figured that if we have enough languages, we've done enough work, then we can have it replicated across many more languages. But we are always looking for collaborators. So, number 4, one of the most common uses of conversational agents is call centers, right? Customer service. And normally you will write a dialogue tree for one customer service, and you write many of these trees for a single company, okay? And what we're saying here is that if you look on the on the internet, a lot of people have written instructions for the consumers to work on the web. Okay, so for example, take Amazon, that's short. If you want to redeem a gift card, you find the claim code, go to that website, and then you enter the claim code and select apply to your balance. Okay? So they actually write it out in natural language. So what we are saying here is that if we are so good at NLP, why on earth do we have to build an agent one by one? We just build one agent that reads all these instructions, okay? And now I can be a call agent for any one of these companies. I read it and I do it. I don't have to train, okay? So that we're going meta. So we read the instructions on the fly and you operate the web for users. And the result of this is that we did this with 22 different online help centers, 80 tasks, 741 instructions. These are all just drawn from the web. And we have an overall accuracy of about 77%. This work includes 2 parts. There's a semantic part that translates the natural language into a formal executable. And the second part is the grounding that takes a description like select apply to your balance, and you have to map it to the element ID in the DOM. Okay, so there is a grounding model that goes with it, and that's why there is a difference between the overall accuracy and the semantic parser accuracy. And all this was trained using synthesized data, actually. And we found that the users prefer the agent over the web. Okay, you just call, and then basically the agent is pushing the buttons for you, and you don't have to go figure out which button it is and what page it is. And interestingly enough, this project is done by Nancy Sue, who was a first-year PhD student with 2 master students, basically, and they did it in 1 quarter. Okay, and this is what we mean. We want to improve the tools so everybody can build interesting agents. But this is not your typical one, but they managed just to, from start to finish, it's just 1 quarter. So next I want to tell you about our Genie project. This is a project that has been ongoing for years, actually. We were very concerned that there are just a couple of monopolies, duopolies, right, who are controlling the smart speaker access. That means that there is not a lot of open competition. And smart speakers are tricky because it sits in your house and it listens to you all the time. And that's why we were very keen on creating the technology that allows many more people to get into it. Because as we said, Alexa has 10,000 employees. There are just not that many companies who can compete. So this project is what started all the work that I was telling you about. It is all about making it efficient and accessible to general, developers, to the general developer community. So at this point, we have built an open virtual assistant And we focus on just the top 10 skills. We can't do all of them, of course. So things like music, podcasts, radio, news, restaurants, search weather, jokes, reminder, timer. It is built on the conversational agent, so by definition, it is conversational. So you can talk about restaurants, like the kind of things that we were just talking about. So, of course, if you have a virtual assistant, you have to also control the IoTs. We have connected to 17 different kind of devices, like thermostat, switch, and so forth. And you basically do the description, and we do a lot of the synthesizing of data, right? This is the reason why we were able to get this far. So we have 17 devices, but we work with Home Assistant. I don't know if anybody here has heard of Home Assistant. It is very popular, actually, with a lot of DIY people. And they have way over 100,000 users. Those are just the registered ones that they know of. It's open source. And what they have done is to build a local gateway that it's a Raspberry Pi, and you can buy it, and it runs in your house. What it means is that it can control your IoTs in the house, and the data will just go from your house to the gateway instead of up the cloud to all the cloud providers, I mean the Alexa and the Google Assistant and the like. So, and on top of that, it is open source. That means a lot of people can write code for it. So for example, if you look at IoT space, you buy a piece of IoT, you have to say, is this Alexa compliant, or is it Google Assistant compliant, or is it Apple HomeKit compliant? Because they all have their proprietary interfaces, okay? So what Home Assistant did was to say, let us connect to the devices directly with the device interface, okay? So they have all the standard Zigbee and whatnot, and they can get the information directly, locally, without going up to the cloud. And as a result, they actually have over 1,000 IoT devices. And I believe that somebody told me, this is not verified, there are more devices that you can get access to at Home Assistant than what you can do on the Apple devices. And the good part is that it doesn't matter whether they were compatible to Alexa or Google. You can actually mix and match, which is one of the sore points for consumers. It's like you have to decide which proprietary framework you want to belong to. And so that's what they have, but they don't have a voice interface. Oh, by the way, when I say the 1,000 devices, they have a meta device. So when I connect to one thermostat, it connects to all the different thermostats that they have in their system. Okay, so that's why even with the device interface we have, we connect to way over 100 different devices. And but they don't have voice built in, and because of the privacy support that we have, they're distributing us as a voice interface on the Home Assistant. On top of that, we also have a very big supporter in Baidu, and they gave us a smart speaker. And they took the software out, but they give us a smart speaker. It is much cheaper than anything that I can do with my own, buy my own Raspberry Pi and so forth. Okay, and it is production level quality, right? So we put our assistant on top of Baidu on that smart speaker. And if you go to our website, you can see a demo of how that works. And we have other partners, like Pico Voice gave us the Wake Word, Yelp gave us access to their restaurant APIs and so forth. So this is a demonstration of how it is possible to have an open source virtual assistant ecosystem. But of course, this is not production level, it's not like production quality, and it takes a lot more engineering efforts that we can't do ourselves, but it is all open source. Okay, so hopefully there is a way for that to grow, and we're very excited to have this partnership with Home Assistant. So let's talk about the sixth one. We said that the virtual assistant should go beyond knowledge workers. So we teamed up with our folks in civil engineering at Stanford, Professor Martin Fisher and his PhD student Jun Wen Zhang. And What I learned is that the construction is the second least digitized industry. You know what the first one is? It's agriculture, okay? So the second is the construction industry, but you know that when we build a building, there is tons and tons of equipment, information, systems, and all that is available. For example, in a 3D model provided by in Autodesk Forge. But these facilities managers, they are on the job. They are hardly tech savvy. Some of them don't even speak English, for example, in America. And we want to be able to put the information in their fingertips. And so the idea is to add voice to it. So Junwen did it in a couple of quarters. And so what he's from civil engineering. And so he was using the methodology, he describes the schemas, he synthesized the code, and then he wrote a little agent policy to go with and then he attached it to this Autodesk Forge, and now it is multimodal. And so one thing we explored is how do we go beyond just doing what the user does, user asks for? Can we use this to provide expertise to the workers? So for example, if you are, I don't know if you can read it, let me make it bigger. So the worker, for example, has to, somebody reports there is a problem with the cooling system. Then they have to go figure out which cooling system it is. And eventually they have to figure out the manufacturer, the model, and the specification, and the manual, and so forth. If you look at the black part, those are the little words that talks about all the information that you can pull out, and then you can go figure out what the model is, and then you go find where the manual is, and so forth. But in the but with voice, the user can just say, I want to search for that. It shows you. And once we know that you are interested in that particular cooling system, we even would say most people want to know the manufacturer, model, and specification. Would you like that? So this is a way to help them with their task. And this is the beginning of a virtual assistant that doesn't just follow your commands. And we just started doing this work, and we have a preliminary user study that shows that 11 out of the 12 people that we asked prefer the expert assistant. And finally, I'm going to talk about a very different project. It really is the reason why I think we will have a socially intelligent assistant before long. This project is with psychiatry at Stanford, and the problem is autism. Okay. 1 in 44 children in the US has been diagnosed with ASD, and they need a lot of training to improve their communication skills. And one of the problems is that they don't show empathy when you interact with them. And for the people who are trained enough to be verbal, to be able to communicate with people, they still are not very good at it, and it turns out that they have the lowest employment rate among all the people with disabilities. Sometimes they are very smart people, but they cannot communicate. They have hard time finding friends, hard time finding romantic relations. And so we were working with Dr. Lynn Kagel, who has been spending 10 decades working with autism. And she told us that we can have exercises to improve their social skills. But there are just not enough clinicians because they need a lot of repetitions. So so we teamed up with her, and I got together a few high school students over this summer, and we built this assistant. We call it Nora, and you can check it out. It's nora.stanford.edu. And it will do exercises with them. So for example, the fonts don't work too well, but anyways, so here's an example. Neuros would do, these are the exercises. It's like, tomorrow is supposed to be warm. And if the user says, gee, I hope I don't melt. And then Neuro would have to grade the response. Okay, this is GPT-3 at work, and you would find answers like, good reply, you sound like you're joking around, and that you're excited for the weather. That means that the sentences are not generic, good or bad. It actually understands that the users are being humorous and provide a very reasonable response. And so we tested it on, we just started, we tested on a few individuals with ASD, and they were very well received. So in summary here is that I want to say that we need to go beyond just AI papers to real assistants that use the latest technology in AI. And we want to build the tools so the developers can focus on the high-level assistant design. How do I provide suggestions, and so forth. And the whole idea is to build it in a different way, and is to say, I really understand what you are trying to say. So we talked about 7 different topics, and as you see here towards the end, we are doing a little bit more and more that have to interact with the users and understanding more softer skills like empathy. So in summary here is that there is a lot of things to do. It's very, very exciting. And GenieScript is all open source, everything from the data sets to all the code, all the skills that we have collected. And we'd love to have people join us. We talked about the multilingual effort, that's an example. And I just want to also thank our sponsors for the support of this project. Well, thank you very much.
Okay. What they can do to join in Spanish project for Taming neural language models?
Send me email.
Okay, okay, let's start.
It's ready to go. We have so much experience now, and we know what we need to do, and you are very welcome to join. I think what I try to do is to involve the researchers in creating the data set, because once you get the data set, there is a lot of work that is specific to the language. Okay, so if you notice all the people that I asked for, these are all different groups doing research. So I think it is a very good way to start, because you will be seeing the semantic parser of dialogues, and I know that we have a long way to go, and you will be collaborating with others, and at the same time, you have a lot of things that only your group can do, because nobody else knows Spanish. You know, Spanish is one of the most used language, so this is something that we totally miss.
I wanted to ask, since I want to know something about this, you know, in GenieScript, is there any documentations online where you can find this? Because I'm quite interested, and I would like also to participate in this project.
So we just finished writing a first paper on this, and we are able to. I'm happy to share with you the draft. This is submitted to. It's just a submission, okay? But I'm very happy to share what we've got, as you know, if you like it. So we are very busy trying to make it usable by others, but all I'm saying here is that if you read it, you have to understand that this is not ready to be distributed. Okay, but I'm happy to show you what we've got.
What happens when the sentence given is not written in a formal way, like using slang or things like that? The message is detected like an error, or it can understand it?
It's whatever the LLMs can do. Okay? So we synthesize and we use the LLM to paraphrase, and then we get more sentences, and then we also use this to fine-tune an LLM. Okay? So because of that, we were able to get the accuracy that we got. So if it is a new slang, maybe it doesn't work, but it actually can, it should handle it because it has been trained on a lot of data and on the internet.
Now, the couple is showing so far the idea of forming the mental language closer to the human. Will it be possible for the genius, like me at this moment? What you consider is the correct to take the path?
I can't really understand you. Maybe you hold the mic a little bit farther.
Con lo que ha mostrado hasta el momento, la idea de formar un metalenguaje para considerar la cercanía a lo que es un lenguaje humano, ¿eso se podría realizar en un futuro con el genio? ¿O cuál sería el camino correcto que podría haber para lo que se está mostrando?
The question actually was if with Genius, Monica, you are able actually to generate text, almost human text, very close to human text.
So right now, because we are scripting what we want is to make sure that the developer can decide on the policy, okay? There are people who worked on neural agent policies, which goes straight from the input to the output. It is all neural. And we don't believe that that is the right way of building a lot of these agents. So they are under the control of the developer, because now they can use recommendation systems, or they can use history to figure out what to say. And after you decide what to say, right now we are just using templates, but we also experimented with using the templates and then sending it through a language model to make it a better sentence. But it is very tricky because you cannot introduce mistakes in that process. So the safer thing to do is to write the code, is to not use the neural network. But as you see there, as you see from the Neura example, it is all GPT-3 speaking. And what we saw is that when we control the conversation to giving comments on users' utterances, it was good enough that we just let it go. Okay, so these are the two extremes. And then you can go anywhere in between. But there is a lot of interesting research to be done.
And I have one last question as well, because I heard that maybe I missed that, but you were talking about GPT-3, and GPT-3 is not totally open, right? What about, have you tried, maybe I missed that one, but have you tried OPG? This is the one that just was released by Facebook Meta, actually in May 20, one must know more about this, but have you tried this one as well?
We have tried a little bit, and the reason, GPT-3 has this instruct GPT thing. It is much more polished beyond just raw. It is not just the raw GPT-3. They added a lot of human data, generating a lot of human data, and it is so that's why it is better. Okay, so one of the things that we wanted to do is to, well, first of all, we want to start with that. We want to see how, what is the state of the art. And we also have started doing research on figuring out a better way of doing instruction rather than human labor. Okay, so that is kind of like a parallel research project, studying how do you make it safer, you know, how do you make it more pro-social and all that. So that is work in progress. And we all, I mean, our goal here is to make sure, is to improve that process so that it is cheap enough that can be applied to the open source software like what we have been doing all along. And I think it is doable. It is just something that we need to do. But we just really want to know what is the best we can do right now. And we did notice that today it is better to use Instruct GPT-3.
Great. Thank you, Monica. And we have just time for one last question, or two questions. First one there, and then we're gonna
En el caso del ejemplo que se dio con la inteligencia artificial, dígame, había un caso en el que el usuario preguntaba si un restaurante es caro, pero ¿cómo la inteligencia artificial en este caso reconocería que un restaurante es caro? Eso, porque creo que ningún restaurante podría reconocerse como tal. En todo caso, ¿cómo sería su forma de pensar ante esto? ¿Cómo reconocería un restaurante caro?
So you gave an example. He mentioned that you gave an example about restaurants, and that the restaurant was expensive. How do you reach this conclusion that it's expensive? What are the measures to say that?
It was just in the database. The database in Yelp, they will tell you pricing, expensive, moderate, or cheap. And we're doing nothing smart in that respect. We're just looking at the database.
Yeah, thank you. And the last question.
Thank you for answering my question. As we all know, language barriers all around the world are one of the main problems of this project. So my question is, how is GeniusScript is going to face these problems, and how they are going to overcome it? If you are going to use some knowledge of native speakers of the German language apart from the institutes?
Native speakers, or so first of all, we don't do ASR. And right now we are using Microsoft ASR. And so I don't really know who is male or female even.
No, I mean,
did I hear you right?
my question is, how GeniusScript is going to face the problems of native speakers?
Native speakers.
Um,
Sorry, native speakers.
Native
Okay.
speakers
Of different languages.
of different languages, yeah.
The answer is open source. Okay, I truly believe that if you make it accessible, all right. So, for example, if you look at the restaurants, just look at restaurants. Every country and language has their own restaurants, and if we get to the point where we just say, look, I already know how to do it in English or in one of these major languages, using machine translation, I will get you maybe within 10% of what we can do in English, then there will be developers who want to take it from there and improve it. And what I would really like to do is to say, we have an advantage. I'm doing everything open source. Okay? Then I think that we can potentially get much more data than anybody else can in a proprietary way. So just take a look at Wikidata. Wikidata is the largest live knowledge base, and that is because everybody is contributing to it, and in many different languages as well. And so this is what I believe, is that voice is so important that it has to have a major open source effort that allows everybody to tap into it, and that's why we've been spending so much time on machine translation. Leveraging machine translation and to make it possible for others, and hence the data set that we are collecting. So for example, we know that, so we've connected to some people like in Africa, and if you get to French, then you can actually get to some of these languages in Africa because they know both, for example. So I think it can spread, and the key here is open source and also tool building. Okay, it is not just the AI researchers writing an example of an agent, and then you have a lot of companies doing them in-house for only the projects that are profitable enough for them to do it.
Well, we are really thankful for your presentation, Mónica, and let's applaud Mónica. Aplausos para Mónica Lam, por favor. Y ahora, siguiendo con el programa, tenemos el paper Preliminary Analysis of Twitter's LGBTQ plus discussions, presented by Abu Nawin. This is the correct pronunciation? Perfect.
Hello everyone, buenos dias. My name is Rafiq. I am from Granville State University, and I co-authored this paper with Abunan Khan, and the paper is titled, as you can all see, a preliminary analysis of Twitter's LGBTQ discussions. So these are the topics, or rather subtopics, that I'm going to talk about. So first I'm going to talk about what's our eventual aim, like what are we starting to do, and where do we see ourselves when it comes to this kind of research, probably in 2 or 3 years' time. I want to briefly talk about the introduction of the research, the related works, the work that have been done in this particular area, what kind of data set we will be working with, the kind of analysis that we have done and presented in the paper, what are the limitations of this research, and then we're going to conclude our talk. So what's the eventual aim of this research? So the way this research starts, and we have been working on this for 1 year now, is to collect data from Twitter. So the data from Twitter that we collected, we did some hashtags and keyword search, and it collected around 8.5 million tweets. So it starts from March 1, 2006, right when Twitter was established, until December 1, 2020, so almost 14 years. So the reason we are trying to do this is that languages evolve, people evolve even. The things that I used to believe in 15 years ago, and that stuff that I believe in now is totally different, because we evolve based on technology, based on new opinions, views, everything. So the thing I'm trying to do is to collect the data, create user communities, or detect rather, communities in Twitter based on following relationships or retweet relationships and so on and so forth, and investigate user behavior in these communities. So once we get these communities, do all communities behave the same? Maybe in one community, LGBTQ plus populations are more vulnerable than the others, or where in other communities, they do get a lot of attacks, but they also have a lot of upstanders. Upstanders means people who stand up for you on those situations. So sometimes people who are more vulnerable, if they see people supporting them as well, they get less vulnerable. So finding out these communities, how do they bully each other or attack each other? Maybe one kind of attack is more prevalent in one community, and whereas in other communities they are not as prevalent. So investigate these sort of scenarios in these communities. And this research is basically the first step towards this goal. We eventually want to go there. What type of topics are more important in different communities? What kind of attacks are more important in online communities, and so on. So why LGBTQ plus communities? These community, LGBTQ plus communities, are more active actually in social media. There have been research found that compared to cisgender communities. LGBTQ plus communities are actually more active in social media. They are more proactive, sharing. They're actually, it was found out that they're actually more comfortable sharing their personal gender associations on social media rather than to actually their parents. So in this research, what we try to do is to use machine learning techniques to understand who are these users who are posting frequently about topics that are more important for LGBTQ plus community. We try to understand what kind of sentiments, emotions, and toxicity levels are in these posts, and to what extent are they there. And also try to understand what is the evolution of the sentiments. What was in Twitter in 2010? Is it the same in 2020? What changed? And so on. So in terms of related works, we try to divide this related work into 3 steps. Obviously, the first step is like online social media behavior analysis has been done with that until now. So like personally, me, I've been working in cyberbullying for 8 years now. I work with Instagram, I work with Vine. Vine is the old TikTok, if you guys remember, but yeah. So vulnerable individuals and communities, they usually express their frustrations, their anger, their fear offline, usually in anonymous scenarios more, because the anonymity actually helps to share your personal feelings. There have been research based on bullying, toxicity, drug misuse, social abuse, bullying, and suicidal behavior as well in social media. So that's one part. The second part is what's the research that's been done when it comes to online media and LGBTQ plus community. It turns out there are quite a few. For example, there's a very cool research that happened during COVID-19. So it has found out that research that LGBTQ plus communities were being discriminated during that time, during COVID-19 pandemic in the US, because of the gender affiliations. User sentiment toxicity analysis has been done in social media as well. For example, Twitter, Instagram, TikTok, negative behaviors like bullying, toxicity, white nationalist propaganda, and religious radicalism as well. There has been some research on analyzing far-right extremists on websites like Parler and Getter using Google Perspective. So this is our data set overview, that kind of data set that we used to collect, or we collected. We did a full archive search from Twitter API from March 1st, 2006. That's when Twitter was founded, until December 31st, 2020. So we collected all the tweets based on the keywords, as you can see on the left. And we did exclude some specific keywords because those keywords are usually used to hijack the topic. So we didn't want to use those things. So those are excluded keywords. And based on those keywords, there are 77 hashtags, 6 keywords, and 8 excluded keywords. We also selected because we did snowball sampling as well, so we used 8 positive organization influencers and 1 negative influencer to collect their data, and then they get their followings and then get their retweets as well. So for hashtag drifting, we use best hashtag, that's a website to identify hashtags that occur together. And also there's a website called Hashtagify that gives you the related hashtags that are not used anymore, but probably was relevant maybe 7 or 6 years ago. So we want to identify those hashtags as well, because we are going all the way back to 2006. So in total, we had 8.5 million tweets, 2 million unique users, and 1.7 million users who had something in their user bios. So user bio means a piece of text that you put on your Twitter profile that helps people to kind of identify like what do you believe in, stuff like that. So this is going to be very important later. So what we do first is we try to identify these users or analyze these users. How are they expressing themselves as in Twitter? If you only have 3 or 4 sentences to write to describe yourself, what are you actually doing this? Like how are you actually describing yourself on the social media? So obviously they are doing this using text, so we wanted to try to analyze those texts. What is happening there? What kind of sentiments? What kind of toxicity levels out there? So as you can see, we used 2 types of analysis. First is sentiment analysis of those user bios, and the second is toxicity analysis of these user bios. So in terms of sentiments, we used distilled word. That's like a very distilled down version of BART. So which was trained, as you can see in the reference, is from Hugging Face. So this Hilbert emotion model was trained with an accuracy of 93.8% on Twitter emotion data set. And the emotion was like, there were 6 basic human emotions. Let me see if I remember. Anger, sadness, joy, happiness, disgust, and surprise. Yes, I did. Okay. So, in total, we found around 640,000 user bios of negative emotions. So for some reason, those users were posting texts on their profiles, and those are inherently negative. That means either anger, or disgust, or fear. So what we did then is that we took these negative bios, that's the 640,000, right? And we tried to see what kind of toxicity levels are there in these negative sentiments. So we use Google Perspective API that takes a bunch of text and tells you what kind of toxicity levels are there. There are 6 toxicities that are threat. That means if you're trying to actively intend to harm someone. Profanity means just using some bad words, doesn't really have to be really bad, it's just profanity. Insult means trying to attack someone or a group of people. Toxicity means posting something that makes someone or a group leave a discussion. And severe toxicity means it's much more severe. They're not just leaving the discussion, but they're not even coming back again. So these are the 6 types of toxicities, and as you can see, there are some toxicities that are, I forgot, identity attack as well. That means attacking someone based on how are they identifying themselves. So as you can see, these are the box plots, and the Google API gives you a probability of 0 to 1. In terms of outliers, identity attackers have the highest outlier and the highest probability as well in terms of distribution. So it kind of makes sense because based on how they identify LGBTQ plus people, it's very natural that they're being attacked with identity attacks a lot. But there are also severe toxicity and threats as well. Threats is very important because threat is part of that forced. That means you're actually trying to hurt someone. In terms of sentiments, as you can see, we saw anger and joy are the most important, or most pervasive, rather. So we also tried to see how active these users are, and to come up with that, we have to how do you quantify activity on Twitter. So we use this definition, TU by DU. DU means how many days that user has been on Twitter, and TU means how many tweets that user has retweets or retweets. We argue that retweet is essentially somebody still being active and supporting that tweet, so that's why you're retweeting. So TU means how many tweets the user has posted since the user has opened that account, and DU means how many days that user has been active on Twitter. Now there's a limitation here because you can open Twitter in 2006 and be deactivated your account for like maybe in the middle 4 years and suddenly you're active. So that 4 years is still counted here. But that's a limitation, just letting you guys know. So based on that, we didn't find a lot of difference. As you can see, the 75th percentile for positive bias, that means users with positive bias, positive sentiment in their user bio, and negative bio means users who have negative sentiments in their user bio. In terms of activity, they're almost similar. I mean, the difference is almost like 2 or 1.5, so that's not much. So that means they are posting around 6 or 8 tweets, respectively. So this is where things start to get a little bit interesting. We tried to understand the evolution, how things were 2007, 2008, and how things are in 2020. As you can see, right around 2010, we start to get a lot of tweets concerning LGBTQ plus topics. Something really happened. And then it really reached probably its peak around 2016, and then it stays there. So what used to be before, like 15 years ago, and what is now, obviously people are much more talking about LGBTQ plus topics in recent years. So as you can see, there are some peaks, and I don't know if you guys can see this, but the peaks are very interesting. They always happen in either October or June. June is Pride Month. I don't remember what is October. But yeah. So significant activity in June and October for Pride and LGBTQ, sorry, it's right on this slide. LGBTQ plus history weeks. So that's when there are the most peaks. So that's when those are the months you get a lot of tweets related to LGBTQ plus topics. And obviously the last decade, you can see a lot of increase in activity. So now we want to see, okay, we did a user bio analysis on this, the tweet analysis themselves. There are 8.5 million tweets. Let's do an emotional analysis, just like we did for user bio as well on the tweets. It's the same scenario, anger and joy are the most pervasive. So that's good. And another interesting thing, we again did this timeline thing with positive and negative sentiments related to LGBTQ, and you can see the blue line on the bottom left, it is increasing. That means the positive sentiment towards this community has been increasing lately. And another good news is the red line is going down. So that means the negative sentiment towards LGBTQ community since 2010 or so, it's been going down. So, and obviously there are peaks. For some reason, the Pride months see a huge spike of positive sentiments, and the bad guys just stop talking about it. So that's a negative sentiment that goes down as a trough. So significant troughs of negative emotion tweets and significant peaks of positive emotion tweets during June and October. So we also try to do some differential analysis. On the top left, you can see the difference. So number of positive tweets minus number of negative tweets. So if it's negative, that means you have inherently more negative sentiment on that month. And if it's going up, that means it's positive, that means you have inherently more positive tweets in that month or time of the year. As you can see, right after 2016, or 2017, at the start of 2017, there has been, and this is the first time in Twitter's history probably, like it did happen during the Pride months, but after that point, something happened in 2017, probably right after the election, US election. LGBTQ plus community topics have been getting more in total, absolute number-wise, more positive tweets than negative tweets, and it's been increasing. So that's good news. And we also try to understand what kind of threats are they getting. So if we try to do a timeline thing of these threats and how are they increasing, are they decreasing, which attacks are on the rise, which attacks are going down. We saw that identity attack was most pervasive, but they have been going down too. If you can see, right after 2017, identity attacks took a bit down to the bottom, and then it stays down. Slowly probably going up, but I would say it's going down actually. And that also applies for the 5 types of attacks too. So eventually it says us, it tells us that there is toxicity, we are not denying that, but it is going down since 2017. There are a lot of limitations to our research. Data collection is obviously done by proper hashtags and keywords, so we only use 77 hashtags and keywords too. So we might have missed a lot of tweets. We only used publicly available tweets. We didn't use any private tweets because of data privacy issues, of course. So we don't have any access to any tweets that are made public or deleted. Only English tweets are collected. So we didn't use any other language tweets as well. So that's another limitation. We use Google Perspective API. They're not on the slide, but obviously we use Google Perspective API. So whatever limitation Google Perspective API has to identify those attacks, this research has those limitations as well. So these are the conclusions. So what did we do? At least the first part of this research we did is that we analyzed our data sets, their bios, their tweets, their sentiments. We tried to do the timeline analysis of threats, toxicities, and identity attacks for these users. And we saw that overall positivity towards LGBTQ plus issues on Twitter has been on the rise. These are the future topics that we try to do, we're actually trying to do right now. So explore the topics of the tweets and user bios with greater granularity. We didn't really delve deep into the actual tweets, the text, which is what we're trying to do. So probably do some kind of topic modeling analysis to see what kind of topics are actually being talked about. maybe do some correlation between these topics and the sentiments. So maybe when it's all about anger, they are just worried about some topics that are not that prevalent for happiness tweets, something like that. We obviously are trying to detect communities on Twitter based on follower-following relationship and analyzing each community's sentiment towards LGBTQ plus issues separately because every community is different. And thank you. That concludes our presentation. These are now our emails. So if you have any questions.
Thank you so much. You have some questions, please?
Thank you for the nice presentation. A question I have is, you identified these emotions, but have you also identified from the tweets which phrases led to those emotions?
Which
Phrases.
Oh, or no, we didn't, again, yeah, that's one limitation of our research, that we didn't actually delve deeper into the text themselves, but that's a very good idea, like what kind of text, what kind of topics are kind of pushing these communities towards this sentiment. That's what's the next level of research, actually. Yeah, that's great.
Thank you.
And I have one as well. Thank you for the presentation. And the other one I saw in one of the slides that you were just computing negativity and positivity, right? What about mutual tweets?
Mutual?
Yeah,
Mutual tweets?
neutral.
Oh, neutral tweets.
Yes.
Oh, neutral. That's a good question. Let's say what we are trying to do is that we are trying to analyze the outliers. Because those are the people who usually like stirring up problems.
Yeah.
Normal people are usually good people, you know what I mean? So we are trying to find the people who are actually causing the problems. Those 3% far right and those 3% far left, like who are actually like causing these problems, and try to understand why they are doing this, understanding those people. Normal people kind of already, we're not really worried about normal people, like so neutral emotions maybe not as much. If you understand the question, yeah.
Thank you very much. And since we don't have much time, ya que realmente ya no tenemos mucho tiempo, vamos a pasar a la próxima presentación. We're gonna go to the next presentation. Thank you very much. The next presentation, it's gonna be presented. Next one is going to be presented by Pablo from Argentina, who is studying in Germany, I think, right?
Yeah, working in Germany, studying in Argentina.
Okay.
Complex situation.
You can go in Spanish if you prefer in Spanish.
As you wish. Yeah, it's written in English, but I could go in Spanish.
I think they will appreciate more if you go in Spanish.
Okay, so let's do it in Spanish. Bueno, como tengo que presentar, soy Pablo de la Universidad Nacional de Córdoba. Vengo a presentar un trabajo conjunto con mis dos directores de doctorado de la Universidad Nacional de Córdoba, Martín Domínguez y Damián Barsotti. Es la continuación de algunos trabajos previos que venimos haciendo en distintos tipos de predicciones en Twitter, ya sea de preferencias individuales o de popularidad de tweets. Muchas gracias. Bueno, para dar un poco de contexto, quiero nombrar brevemente de dónde venimos, cuáles son nuestros trabajos previos y qué nos lleva al trabajo que presentamos ahora. El primer trabajo que hicimos en esta área es un trabajo de predicción de retweets de un usuario basado en el comportamiento de su entorno social. Sorprendentemente en aquel trabajo, sin incorporar características del contenido, sin hacer en el PIN, logramos una calidad de predicción bastante buena, de un 87.6% de F1. Y bueno, fue el punto de partida para otros trabajos que hicimos después. Luego, en este mismo trabajo, evaluamos incorporar características del contenido y lográbamos una mejora de un 1.7% en usuarios que tenían menor performance en estos modelos basados solo en información social. Pero una limitación de este primer trabajo es que todo el estudio estaba basado en desarrollar para cada usuario para el cual queríamos predecir sus preferencias de retweets un modelo independiente, o sea, los modelos estaban centrados en el usuario a predecir. Entonces, por eso y por limitaciones de los modelos que usamos en esa época, este trabajo tiene ya más de 5 años, es un trabajo que solo se pudo desarrollar en una selección de 200 usuarios a modelar. Luego, el año siguiente, desarrollamos otro trabajo que se trataba de un problema totalmente diferente, que era predecir popularidad de tweets, ya no retweets de un usuario individual o no, sino su popularidad dentro de una comunidad, tomando como características sociales el comportamiento de ciertos influencers que seleccionaban. Entonces, esto fue en cierta forma un avance en el sentido de hacer un modelo más general, pero también un modelo que da predicciones más generales. Lo que nos interesa ahora es un poco juntar ambos mundos y ver si es posible tener un modelo que dé predicciones individuales, pero que de alguna forma modele el entorno social de un usuario de una forma genérica que pueda ser generalizable e incluso aplicable a otros usuarios. Y luego, para completar, bueno, cabe mencionar que el trabajo este de 2018 fue presentado también aquí en Simbi, y en 2020 con uno de nuestros alumnos de doctorado hicimos otro trabajo en el que básicamente se estudiaba el impacto de la temporalidad en los dos trabajos anteriores, o sea, cuál es la relación entre la calidad de la predicción y el tiempo transcurrido desde que se generó un tweet para el cual estamos tratando de predecir o popularidad o retweet de un usuario individual. Bueno, con este contexto puedo pasar a contarles más detalles del trabajo actual. Empezamos describiendo cuál es nuestro set de datos. Estamos, como hay un énfasis fuerte aquí en comparar este modelo general que vamos a implementar contra los modelos individuales del primer trabajo, el set de datos que usamos es el de este primer trabajo, que aquí describimos cómo se construye. Lo que hicimos es a partir de un usuario inicial, tomando 3 pasos de la relación seguir dentro de Twitter, construimos un grafo universo que tenía varios millones de usuarios, pero en aquel trabajo original nos interesaba tener, para cada usuario para el que tomáramos predicciones, tener una representación más o menos homogénea de su entorno. Entonces, teníamos un método para construir un subgrafo en el que cada usuario tenía por lo menos 50 vecinos en su entorno, y eso nos da un grafo de alrededor de 5.000 usuarios y 230.000 áreas. Este va a ser el punto de partida de todos los análisis que van a ver, pero también haremos algunos refinamientos extra por nivel de actividad y otras cuestiones. Y en cuanto al contenido, porque en definitiva lo que aquí estamos queriendo modelar es las preferencias de contenido de cada usuario, qué decide cada usuario retuitear o no. Lo que se tomó es un mes de tweets en español de los timelines de todos estos usuarios en un periodo simultáneo de tiempo, y eso nos dio un set de datos de alrededor de 1.600.000 tweets. Con esto podemos pasar, ya teniendo los datos, a formalizar nuestro problema de predicción de retweets. La idea en general va a ser dar un usuario y un tweet posiblemente visto por este usuario, esto lo tenemos que formalizar. El objetivo es predecir si este usuario U retuitea el tweet T, y la entrada va a ser qué usuarios dentro del entorno de este usuario que estamos observando retuitearon este tweet. Tenemos acá dos conceptos que hay que formalizar de alguna manera, que es que un tweet sea visible, que en nuestro caso elegimos tomar como visibles aquellos tweets que son escritos por usuarios seguidos por el usuario que estoy analizando y excluyendo los posibles retweets del usuario original, porque estamos enfocados en predecir retweets y no en los tweets propios. Obviamente, bueno, esta forma de definir visibilidad tiene sus limitaciones, porque en definitiva el hecho de que un usuario que yo sigo haya publicado en su timeline no es una garantía de que yo lo haya visto, sobre todo, digamos, si sigo muchos usuarios. Pero bueno, fue una simplificación que decidimos tomar y igual obtenemos buenos resultados. Para limitar el tamaño de los datasets, sobre todo considerando que este dataset originalmente se trató con modelos de supervector machines que eran bastante pesados de entrenar, entonces de la mayoría de ejemplos negativos que hay de tweets visibles pero no retuiteados, si había más de 10.000, en general decidimos limitar a 10.000. Bueno, y el otro concepto que necesitamos formalizar acá es a qué consideramos entorno social de un usuario. Y para estos trabajos siempre hemos estado tomando el grado 2 de la relación seguir. O sea, los usuarios que nuestro usuario central sigue y los seguidos por él. Y por último, también por una cuestión de tener suficiente riqueza de datos, decidimos filtrar usuarios que sean demasiado pasivos en el periodo que estudiamos, o sea, en nuestro caso los que tengan menos de 10 retweets, y a su vez los tweets que son solo compartidos por este tipo de usuarios también se remueven. Entonces esto nos deja un subconjunto del grafo G de 5.000 usuarios que habíamos nombrado antes, de alrededor de 3.200 usuarios. Y esto es importante porque va a condicionar cómo partimos nuestro set de datos para entrenamiento y evaluación. En el trabajo original, como se entrenaban modelos independientes por usuario, se tomó una selección de usuarios activos y centrales de alrededor de 200 usuarios. En el trabajo que estamos presentando ahora se van a modelar todos los usuarios, pero es importante seguir distinguiendo estos usuarios para poder comparar los resultados. Bueno, entonces con esto pasamos a el particionado de nuestro set de datos, que tiene que cumplir con 3 requerimientos que nosotros tenemos para evaluar este trabajo. Uno es la posibilidad de entrenar en datos del pasado y evaluar en datos del futuro. El segundo requerimiento es tener la posibilidad de evaluar nuestro modelo en usuarios que no fueron vistos previamente. Y tercero es también tener la posibilidad de comparar los resultados del modelo general que vamos a implementar contra los modelos individuales que teníamos previamente. Entonces, juntando todos esos ingredientes, tenemos esta partición que se ve un poco compleja, pero no lo es tanto. Recuerden que bueno, en total tenemos unos 5.000 usuarios en nuestro grafo. En el trabajo original teníamos este conjunto U de usuarios activos y centrales, y en el trabajo actual vamos a incluir el resto de los usuarios también para generar predicciones. Entonces lo que se decidió hacer es, para cada usuario, los tweets de su set de datos visibles, de donde vamos a predecir cuáles son retweets y cuáles no, fueron partidos en un 70% de entrenamiento y 30% de evaluación temporalmente. O sea, son los primeros 70% y los últimos 30%. Eso a nivel de tweets. Y a nivel de usuarios, se tomó dentro de los usuarios activos y centrales de los que teníamos en modelos individuales en el trabajo previo, se los partió en dos mitades, y al resto de los usuarios los partimos en 70% y 30%. O sea que la situación acá es que tenemos, digamos, tenemos usuarios de entrenamiento y usuarios de evaluación, pero dentro de cada usuario tenemos tweets de entrenamiento y tweets de evaluación. Para simplificar un poco, la idea con la que hay que quedarse aquí es que el modelo que vamos a presentar está entrenado en las dos regiones verdes, digamos, todos los tweets de entrenamiento de los usuarios de entrenamiento, ya sean de los activos y centrales originales o de los usuarios más generales. Bueno, y con esto vamos a pasar a presentar cuál es el modelado de la actividad del entorno de cada usuario, cuál era el trabajo original y qué es lo que estamos proponiendo ahora para lograr tener modelos que pueden consumir datos de distintos usuarios centrales y ser aplicados a nuevos usuarios. El esquema es muy simple. En realidad en el trabajo original lo que teníamos era, para cada tweet teníamos una matriz booleana de unos y ceros, donde simplemente marcábamos con uno dentro de los vecinos del usuario que estamos estudiando que quiénes dieron retweet o no. Y el objetivo era, para el usuario estudiado, predecir si hay un retweet o no. Como verán, bueno, esta representación claramente depende del usuario central, porque en definitiva la cantidad de columnas es la cantidad de usuarios en el vecindario de U. ¿Cuál es la propuesta de modelo general que planteamos ahora? Es, dado un usuario central, podemos ordenar sus vecinos por alguna métrica de importancia, que no vamos a dar detalles aquí, pero en nuestro caso estamos usando un promedio entre nivel de actividad y nivel de centralidad normalizadas. Y una vez que tenemos ese rankeado de los vecinos, podemos decidir tomar los primeros K como usuarios distinguidos, para los cuales vamos a mantener estas características booleanas que tenemos antes, y al resto los agrupamos en B grupos por nivel de importancia. Y en cada uno de estos grupos lo que vamos a hacer es agregar por suma, o sea, en lugar de tener estas features booleanas de antes de si hay retweet o no, las características ahora pasan a ser cuántos retweets hay en cada grupo. La ventaja de esta representación es que, independientemente del usuario central que tomemos, el largo del vector es K más B, que son, bueno, dos hiperparámetros que podemos elegir, pero nos dan una representación independiente del usuario. Estamos un poco cortos de tiempo, así que voy a apurar un poco a los resultados. Bueno, el modelo de clasificación usado es XGBoost, que también es un cambio respecto a trabajos anteriores que usaban Supervector Machines. Y lo que se realizó sobre tomando este modelo, realizamos un ajuste de hiperparámetros conjunto entre los hiperparámetros de XGBoost y estos nuevos hiperparámetros de modelado del entorno, o sea, la cantidad de usuarios distinguidos y la cantidad de grupos. Acá pueden ver cuáles fueron los intervalos de búsqueda y la configuración óptima encontrada. Y con esto, una vez que tenemos estos hiperparámetros óptimos, entrenamos modelo final en el conjunto de entrenamiento que les mostré anteriormente, que son unos 7,5 millones de pares usuario-tweet. Bueno, y para ir concluyendo, algunos resultados de evaluación. El F1 sobre todos los datos de evaluación, o sea, todo lo que no era verde en la tabla que mostré antes, es de un 83,9%. Y también podemos comparar con los modelos individuales. Acá pueden ver un histograma sobre este conjunto de alrededor de 200 usuarios distinguidos de cuál es el F1 del modelo general limitado a los tweets de evaluación de cada usuario versus lo que daba para ese usuario su modelo individual. Y bueno, observamos que en promedio es un 2.2% más bajo, pero si vemos la distribución en la mediana y en el cuartil superior, el comportamiento es bastante comparable, o sea que en definitiva el modelo general para usuarios para usuarios más predecibles tiene una performance comparable, y solo para usuarios en el cuartil inferior vemos que hay una diferencia un poco mayor de 2.7%. Y para concluir, también hicimos un análisis de cómo se comporta el modelo en usuarios conocidos versus usuarios desconocidos durante el entrenamiento, o sea, usuarios de training contra usuarios de test. Y en general, bueno, no observamos diferencias significativas entre usuarios de training y test, porque el modelo parece estar generalizando bien. En lo que sí observamos una diferencia que es esperable es en la performance en los usuarios U, que eran estos usuarios seleccionados activos centrales en el trabajo original, versus los demás usuarios B, que bueno, son usuarios más generales y pueden contar con menos información. Bueno, para concluir, la principal conclusión es que bueno, una representación estándar de la actividad social del entorno de un usuario puede dar una buena calidad de predicción, con un modelo que es más rápido de entrenar, más generalizable y en general certificando muy poca calidad de predicción. Incluso, como dije recién, pero la mejor mitad la calidad se mantiene. Y bueno, otra conclusión es que XGBoost también es un buen modelo para este tipo de problemas. Los resultados de los modelos individuales están alineados con lo que teníamos antes con modelos de Supervised Machines, pero con mucho menor tiempo de entrenamiento. Y en términos de próximos pasos, bueno, hay distintos aspectos del problema que se pueden modelar con modelos más sofisticados, como la temporalidad de los tweets, o incluso la actividad del entorno a través de Graph Neural Networks, que de hecho era la motivación de este trabajo inicialmente. Esto es un modelo baseline para ese trabajo, pero los resultados fueron bastante buenos, así que aquí estamos mostrándolo. Y bueno, después sí, agregar modelado de contenido y entender mejor también la relación entre la cantidad de actividad previa de un usuario y la calidad de las predicciones. Y bueno, eventualmente también extenderlo a otras redes sociales, pero bueno, siempre es difícil alejarse de la comodidad que da la API de Twitter, que sigue siendo la más conveniente para este tipo de estudios. Bueno, muchas gracias por su atención.
Una pregunta por allá.
Sí.
Muy buenos días. Quisiera saber si estos modelos predictivos podrían tener una aplicación en el ámbito de la publicidad para hacer lo que debería ser anuncios más efectivos y que puedan llegar a una mayor cantidad de personas o algo similar.
Sí, potencialmente creo que dar una buena medida, o sea, este F1 de la predicción basada en el entorno social para un usuario, de alguna manera da una medida de qué tan influenciable por su entorno es el usuario elegido. Entonces, en ese sentido podría usarse para hacer targeting, de básicamente seleccionar usuarios más influenciables por su entorno que otros, de alguna manera.
Bueno, muchas gracias. Estamos retrasados. Thank you very much, Pablo. Now we're going to have our coffee break. Por favor, aplaudamos a Pablo nuevamente. For the coffee break, we should go that way, to my left. Y por las participantes, for the participants, please go to the right, o por la derecha. Todos los alumnos participantes por la derecha, por favor. Para el coffee break, la pausa de café, gracias.
Hola, 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 hola. Hola, buenas. Oye, pero no tengo... Le he cambiado tu capturadora, pero no me sale el audio. No puedo probar acá.
¿No pica?
No sé si pica, tendría que abrir el audio.
Ábrelo, pe.
¿Y si me escuchan?
No importa. Si está en coffee break, no te hagas nada.
En breves momentos continuamos. No pica. Hola, 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 hola. Hola, 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 hola. No me agarra el audio. Si no vas a tener que hacer eso, ¿ah? Y ella que se coloque acá, porque... Sí, sí. Estamos probando ahorita algo a ver si sale directamente para la...
Sí, sí, probando.
No quiero ese micro. Pero no, en la cámara llega, pero no me sale en la transmisión. ¿Cómo?
Pero que tenga.
Es que no puedo probar.
Que tenga todos. Se puede cruzar.
Pero ella tendría que ser acá.
Claro, que la cámara tiene que tener una salida para tu.
Ya lo saqué con la capturadora. Deberías tener, he capturado. Tengo la imagen.
La imagen, pero no el sonido.
Pero cuando he capturado la entrada de sonido.
¿Y ahí ya lo modificaron y lo configurado?
Sí, nada. No pica. Está en ambiental. A ver, cierra tu audio. No, espérate, no, al final si no vas a tener que salir. Cierra tu audio. Sí, cierra, silencio. Quiero saber.
Este de acá, ya. Pero que resultó lente al
presentaciones. Ahora tenemos a Kevin Rivera y a Diana Quintanilla, ¿cierto? Que nos van a presentar Segmentation and Classification of Pages for digitized documents of the Public Prosecutor's Office. Bueno, ahora tenemos, now is the next presentation by Kevin Rivera and Diana Quintanilla, and let's welcome the authors, please.
¿No será mi mental?
Sí, ¿qué has hecho? Pues yo estoy grabando, por si acaso.
Good afternoon, everybody. In this opportunity, is present the segmentation classification page for digitized documents of the public prosecutor. The content of the presentation are the problem, objectives, related work, methodology, segmentation, classification, contribution, and result, and conclusion and conclusion. This work is focused in judicial case, the public prosecutor. The problem is the organization. The office prosecutor. Imagine is the documents in any office in the public prosecutor. The first objective is ensure the optimization of resources during the digitized documents of the public prosecutor. The second objective and third objective is obtain the best model for page segmentation, obtain the best model for page.
text features and layout features. In the page 1, you can see the label start is page is start the document. The page 2 is the part the document. And the color green is text features, and light blue color is the layout features. In total, the dataset for the work is obtained 1,071 rows on 1 bit, and 70% for training. 70,000 for training and 30% for testing. In the segmentation page, I'm using the machine learning algorithms. In total, using the 9 machine learning algorithms, and the best result is random forest. The 93% for accuracy, 95% for sensitivity, in 93% for precision. With respect to classification, using the regular expression, in total identify 27 document types, and for each document type is a regular expression. For example, in the code A is a file, the code B is a resolution, etc. High accuracy in the classification of document types above 90% accuracy using regular expression. And you can see the result and the segmentation and classification. The number page is a result the segmentation. In the name of file, name file is a result the classification. For example, in the right, and the page from the page 2 to page 3 is officio or office. This page 2 to 3 is a result the segmentation. In the name of the file is a result the classification. And in this slide, I pass to my partner Dia1.
Good afternoon, everybody. To summarize, in this work, using a binary classification for segmentation tasks, we use test feature and layout feature from the literature and identify that the standard deviation of the left margin per lane was one feature with more importance. Also, we identified that it's not necessary to use the full content of page, because the feature with more importance only use the top content of page. For example, the first n lines, the header or top content. Okay, the layout feature is very important where the OCR, optical character recognition, don't extract characters correctly. The text is confused. We conclude that our best model we deployed our model as a web service where our initial test achieve the time processing of initial test is 1 second per page. Is correctly timed, and our server have 4 gigas of RAM. Also, as a future work, it's necessary a public dataset, because a public dataset permits a comparison more effective. Additionally, For some documents, by example, document number identification, is necessary image processing, for example, a binarization. Thank you.
Thank you so much. Is there some question from the audience, please? ¿Alguna pregunta?
A ver si nos pueden sugerir qué pasos tomarían para mejorar la precisión, considerando que muchas veces los documentos, contratos, muchos otros documentos oficiales vienen, digamos, con líneas, por ejemplo, con líneas que los atravesan, ¿no? Atraviesan las líneas de los montos o de otra información que es clave, ¿no? Entonces, ¿cuáles serían sus siguientes pasos para mejorar esa precisión en la captura de datos cuando tienen esos problemas?
Comúnmente, sobre todo con documentos antiguos o documentos que están almacenados así físicamente por mucho tiempo, están deteriorados, por así decirlo. Entonces, como comentamos, añadir procesamiento de imágenes permite la limpieza de estos documentos, quitar las líneas, también la orientación, hacer técnicas de subir la calidad del proceso de la imagen escaneada. Entonces, con eso, el componente de OCR puede detectar con mayor efectividad los caracteres. O sea, en sí se puede aplicar más técnicas de procesamiento de imágenes, pero sería como que un paso dentro del flujo de la segmentación.
Bueno, muchas gracias. Thank you very much. And we're gonna go to the next presentation. Next presentation.
I'm back. No. I'd like to introduce our next speaker. It is my pleasure to introduce Dr. Liman Okoglu. And she is the Heinz College Dean's Associate Professor of Information Systems at Carnegie Mellon University. She has received her PhD from Carnegie Mellon in 2012, and her research interests are in machine learning and data mining. Let's hear from Liman. Oh, there.
Hello, everyone. Can you all hear me well at the back? Good. So thanks for the introduction, Monica. I would like to thank Antonio and Juan for inviting me. It's a pleasure to be here. Very excited to share our recent work on Medicare fraud detection today. Just a little bit about me. So I work on anomaly mining with real-world applications to fraud detection, and I've studied fraud detection in various domains, including advertisement fraud, accounting fraud, bank fraud, and this year we actually were lucky to get access to the US Medicare database, and we decided to see if we could find some suspicious providers doing suspicious things. So the two important keywords in my title is unsupervised and explainable. So we want to do fraud detection in an unsupervised setting, meaning that we do not want any label supervision or collect any human label data, just find unknown phenomena. Explainable here means that anomaly detection cannot be automated, meaning that we cannot directly take the outcome of an anomaly detector and just go lawsuit those providers. Rather, an auditor needs to go through the process of verification, and explanations here is to guide them to do proper verification before any criminal charges can be imposed. So this is joint work with my collaborator, Larrabure, who's an economist at Boston University, and my PhD student, Shubhranshu Shekhar, who is on the job market this year. So let me give you some background information. US healthcare spending is enormous, so it's in the trillions every year. And just to give you a sense, in 2019, the US healthcare spending was as large as the world's fourth largest GDP, which is of Germany. And of this, a significant portion goes to Medicare spending in hundreds of billions. And Medicare is this government insurance program provided to elderly, 65 years or older, as well as the disabled. And according to the statistics, the healthcare spendings, statistics by Centers for Medicare and Medicare Services, the growth of spending is going to increase at a rate that is outpacing the growth of GDP. So if I've learned anything, I don't know why the slides are showing, but we'll have to overlook the issue with the slides, I guess, with a different computer. Hello everyone again, let me continue. So lots of money being spent on healthcare in the US, hundreds of billions on Medicare, and if I've learned anything, wherever there is money, there is fraud, is that right? So advertisements, a lot of money, a lot of fraud. Tax, money involved, tax fraud. Accounting from finance, banking fraud. So just like that, Medicare has defined certain practices to be fraudulent, such as providing false claims, representation of fact, such as charging excessively or unnecessarily for certain medical services and supplies, misusing codes on which you use to code the diagnosis and procedures employed on a patient. Other forms include kickbacks, bribes for certain referrals to certain physicians and so on. So in this work, we will try to detect anomalous conduct by providers or hospitals that lead to higher payment levels without actually focusing on what type of fraud particularly they are committing. And estimates of loss goes to about 1 to 5% of all billings, as estimated by experts, although the exact amount is unknown because fraud is hard to detect and measure. And this translates to tens of billions of dollars for Medicare annually. So the US government enforces certain anti-fraud tools. So these include criminal and civil enforcements. On the criminal penalties, and there are federal healthcare fraud statute, kickback statute, wire fraud, and racketeering statutes, and so on. In addition to criminal penalties, there is also civil enforcement through what is known as the False Claims Act. Here, the government incentivizes whistleblowers to come forward. So let's say you're a nurse working in a hospital and you know some suspicious activities are going on, you can come forward, and the incentive is that you receive compensation in the form of 1%, and that also translates to several $1 million. So there is good incentive. There is other programs such as recovery audit contractors. Without going into the details of anti-fraud enforcement, I would like to place our work in the scope of detection rather than prevention, and these are our approach is complementary than to existing auditing practices. So here's the outline. I would like to give you a good background and understanding of how Medicare payment system works, because just like in many different forms of fraud, the ecosystem really matters into how the fraudsters identify loopholes, and depending on the domain, this looks very different, so we need to start by understanding the ecosystem. And this includes how the payment system works, so I'll give you a little bit of background, and then I will introduce the claims data that we use, as well as the detection approaches. So Medicare payment system is what is known as this PPS, prospective payment system, which is different from fee-for-service. Rather than you pay for what you get, here there is a predetermined fixed reimbursement scheme. For example, if someone gets a kidney surgery of certain kind, any hospital providing that particular treatment is going to get a fixed reimbursement. And this incentivizes to keep costs down, because at the end of the day, the profit the provider or hospital is going to get is the difference between this fixed reimbursement that they get minus the treatment cost. So treatment cost lower, profit higher. But then this would, on the negative side, incentivize them to avoid treating high-cost patients, right? So to that end then, there is some adjustments allowed on top of, as additive factors on top of the fixed reimbursement. And these adjustments include factors like the wage index, is the hospital in an expensive area like Boston, the patient case mix, meaning is the hospital treating disproportionately more heavily sick patients, disproportionate share of income, low-income patients, length of stay, as well as some big outlier cases that needs high-cost treatment. So at a high level, what I would like you to remember is this flow of dependencies. So upon admission, a patient comes into the hospital, the physicians are going to write down on the medical chart of the patient the conditions and the services they are treated to. And then a medical coder is going to get the medical chart and translate the diagnoses and applied procedure as coded by the physicians into what is known as ICD codes. Okay, so chart dictates ICD codes. These stand for International Classification of Diseases System, that provides certain numbers, system to code certain diseases. And then the ICD coding directly directly translates to one single Medicare Severity Diagnosis Related Group code, or DRG code. And this DRG is exactly associated with this fixed dollar of reimbursement that I talked about earlier. Right? So whatever procedures and diagnoses a patient receives are in the ICD code, and realize there are different agents here. There is the physicians treating, and there is the medical coders, and then all these ICD codes translate to a single DRG with a fixed amount. Right? And one kind of that trying to play with the ecosystem in a way with the codes or the patient charts, such that it leads to a more expensive DRG code with a higher fixed reimbursement amount. And just to note here that actually these medical coders are human coders, but they use what is known as specialized grouper software that will prompt them to actually encode any comorbidities or other complication that reminds them that can allow, if coded, that can allow for a higher DRG billing. Here's some examples of DRG codes. So some DRG codes, for example, simple pneumonia and pleurisy, this is 195, and then they actually within DRG, multiple DRGs with different complication and comorbidity levels exist. So without complications and comorbidities, with CC or with major CC are different DRG levels, just to give an example. There are also some DRGs that are more catch-all. I will visit them later in my case study. So those are classified under other. So anything that is ambiguous or unlikely to be fall into any particular DRG that's very specific, it can be filed under other injury and poison and toxic effects. And these DRGs are further classified higher in the hierarchy under what is known as the MDC, or Major Diagnostic Category Groups. And there are 25 of them. As such, they fit in the entire slide. So here you see that each one corresponds to typically one major body system, such as digestive, respiratory, and so on. So take the first one, for example, diseases and disorders of nervous system. All the DRGs with 20 through 103 fall under the MDC, and so on and so forth. Right? So there is a lot of structure, and there is a lot of information or documentation as to how the medical coder should use to code any particular claim. Here's a breakdown of the payment that will show up in your medical claim. So the first driving factor is this DRG code, as I said. That dictates the fixed reimbursement amount, and plus some adjustments as highlighted in blue in my slides. So the MSDRG here will be changed or adjusted according to the hospital wage index. Is it in an expensive geographical location? As well as the case mix. Is this hospital treating mainly more sick patients than others? And then there will be additive factors, such as, is the hospital a teaching or research hospital? Are there disproportionately low-income patients this hospital is treating? What is the length of stay, and is this an outlier case? So these are all additively compounded on top of the bill, but what is mainly driving is this DRG code. So this is a breakdown of everything. I'm not going to go into this slide, but if you're interested in where the different parts of the dollar amount is coming, we can talk more. Here's another view. So what we're interested in the payment amount, because at the end of the day, the hospitals are trying to make more profit. And these are dictated by mainly the diagnosis-related group. This is another view of the previous chart, essentially. There could be other additive factors like outlier payment, disproportionate share, indirect education and teaching. And the DRG itself is dictated by these ICD diagnosis codes as well as procedure codes. And these are further dictated up in the hierarchy, right, by patient demographics, medical history, and their true health status that we don't get to observe. Right? So all of these dictate the ICDs, which is the DRG, which is the payment. So then we can actually see it's the different agents in the ecosystem to proctor with different parts of this payment system to gain more higher levels of payment. And here I'm giving you some example manipulations, highlighted in colors and letters. So starting with A in red, so you see these arrows. A medical coder can mislabel a DRG, basically trying to get to a higher, more expensive DRG, from patient demographics, medical history, diagnosis, and procedures by coding them in a certain way, in a grouper way, so as to end up with a more expensive DRG. That's called upcoding. The outlier payments can be manipulated on this side. the hospital can decide to keep the patients longer than 3 days, which is the typical, to generate more profit from the inpatient hospitalization stay. The disproportionate share of payments can be manipulated. The patients can be kept for a short hospitalization stay, even though they didn't need it, so this is a waste form of abuse. And finally, the codes themselves can be coded in a way that is not actually reflective of the truth. So the medical coder can code certain ICD treatments and diagnoses that were not actually performed. Okay. So having understood a little bit of the payment system, let me tell you a little bit of what data we are using. So in this database, we have access to the entire history of Medicare claims, and particularly we are going to focus on the 2017 snapshot, around which the ICD coding practices sort of changed. And so here, just to give you an idea of the statistics, in 2017 alone, medical total expenditure was 700 billion plus, and the number of inpatient beneficiaries or patients were in millions, 6.6 million. The claims that we are going to process just in 2017 is 11 plus million. And there are about 7,600 hospitals all around the US. So in addition to the data in to reflect sort of the status patient characteristics of their health status. So we use here all the inpatient and outpatient claims from these last 5 years, indicators of chronic conditions a patient is associated with, their demographics, as well as some office visit metadata that we have access to. And all these sources are also very large scale. So we have hundreds of physician visits and hundreds of outpatient visits every year. We also know a lot about the providers. These providers, 7,600 hospitals all around the US, are well identified through certain identifiers that we can link to different databases. And we know their type of ownership, we know whether they're public, private, or government hospital, whether they're academic hospital, and all these meta information about the type of hospitals. And in order to quantitatively evaluate whether we are detecting anything meaningful, we are going to use the Department of Justice press releases. So the Department of Justice releases certain cases that went to lawsuit about providers in their press release on their website publicly to inform the public and warn any future such conduct. And we will scrape the database to collect releases that mentioned hospital names, and we'll treat them as ground truth labels based on partial name matching. I'll talk more about the ground truth when I show you some results. So before I go into the details of how we do detection, just for fun, let's do some data analysis. Okay, so something simple we wanted to do, and I want to show you some very beautiful data plots, if you will. So here's what we started with. Remember what I wanted you to remember, right? Medical chart of the patient informs the ICD code, which informs the single DRG code associated with a fixed reimbursement amount. So here there is a lot of dependence between ICD codes and what DRG they dictate. So just for fun, let's take all the data and build this DRG by ICD matrix, right? Filled with counts, right? So basically, take all the claims, they each associate with a single DRG, right? And a bunch of set of ICDs. How many times an ICD code was used in a claim with a certain DRG, right? That's this matrix is all about. And let's just do some simple singular value decomposition of this to find structure, right? And by what structure means for SVD is that this data comes in, it is decomposed into two smaller matrices, the multiplication of which gives a good reconstruction of the original matrix, right? And you can think of this as, these little matrices on the left composed of left singular vectors, on the right singular vectors as the rows. And if we multiply the ith left singular vector with the ith right singular vector, we get a matrix, intermediate matrix. And you do this for all 1, 2, 3 in this example. Left and right singular vectors to get these rank 1 intermediate matrices, the sum of which is the reconstructed data, right? So this is simply just matrix-matrix product through outer products. Right? So what does structure mean here? So these singular vectors are expected to capture structure in the form of dense submatrices, right? Just to break down here, if the original matrix have these very good structure, dense submatrices, the left singular vectors are orthogonal to each other and will look something like this, right singular vectors associated with like this, such that these rank 1 intermediate matrices reconstructed by the outer product of the ith left and ith right singular vectors will depict each and every dense subblock, if you will, the addition of which will reconstruct the original matrix, right? So this is going to automatically, essentially, is going to find these dense blocks if they exist in your data. That's what SVD is going to do. And if we do SVD on our data and take these left singular vectors, which are it's a DRG by ICD matrix, so the left singular vectors are DRG, associated DRGs, and plot the values for the DRGs of the first and the second singular vectors, this is what you see. I don't know if you've looked at these plots before, but this is as good as it gets. It's beautiful because it's exactly orthogonal, and a lot of things are 0, right? Some DRGs have high values on the first component but 0 elsewhere. Some others have high values on the second component, 0 elsewhere, which means that there are very strong these matrices, dense blocks that I've shown in this data, right? And when you look at these DRG codes in each cluster, you see that they are very related, right? All of them are heart conditions in this cluster, all of them are stomach and digestive system DRGs in this one. If you look at the third one, we identify the bone, knee, spine related DRGs. So just to say that there's a lot of structure, and this is mainly coming from the way the system is organized to be very strictly coded, right? So you can only use certain ICD codes to code, I don't know, knee injury, for example. Similarly, we can look at the right singular vectors, which are ICD codes associated with, again, as good as it can look with the real data. Okay, so the values here with high values are ICD codes clustered under the first right singular vector. And if you look at the description, text description of these ICD codes from the system, and look at the word cloud, we quickly recognize that, okay, these ICD codes associated with certain DRGs under the MDC system of circulatory system. And the second one, similarly, if you look at the word cloud, right, it's all about digestive system disorders, and we can keep doing this, but there is so much structure, meaning that the way things should be coded are very well specified. That's only what it is reflective of. So any deviations from these coding practices, we should be able to catch, because there's a lot of patterns in this data, right? It's far beyond random data, right? So at a high level, then, the Medicare anomaly detection problem here is that we are given lots and lots of claims associated with various providers, and each provider has a set of, each provider I has a set of NI insurance Medicare claims, right? And associated with a database of beneficiaries or patients. So it's basically a set of claims as coded with ICD and DRG codes. And the goal is to build an unsupervised detection system that will give scores at a provider level, right? So we are trying to identify suspicious hospitals or providers that are having some aberrant spending behavior. So at the end of the day, whoever is making more money for unexplainable reasons will be flagged, irrespective of agnostic to what type of fraud they may be doing to increase their payment levels. And we want this system to be unsupervised, provide explanations to human auditors, and also be scalable to the millions of people who will be processing. So now I'm going to go into the technical details of how we do the detection. And before I do any details, I want to give you an overview of what we did. So we actually took a multi-view approach, mainly because I was collaborating with an economist and they had a different viewpoint than I do, and eventually we ended up with three different approaches to the detection problem using different data modalities, as I denote here with D1, D2, and D3. So let me explain. In the past, and then we're going to try to predict their spending in the current year, in 2017, in dollar amount, through their medical history. So here we are also going to add the hospital identities and the number of times they visited this hospital in 2017, to account for the fixed effects of just visiting that hospital, fixing everything else, adds or subtracts dollars from your total payment. Okay, so this is a global level regression. The second approach uses a different data modality. We will actually go into the ICD space. Right? So here we're gonna, rows are different, notice, beneficiaries here. Here rows are hospitals. So for each hospital, we are gonna study how often and how frequently, how they use ICD coding in 2017 and do some subspace outlier detection. And this approach is local because, right, there are, I will tell you, 40,000 ICD codes, and it's not meaningful that the hospital will be proctoring with all of them, right? There will be some covert behavior, so we are doing, looking at suspicious behavior in some subspaces, so this is local in the columns, if you will. And the third view is, again, we're going to do suspicious behavior detection at using a peer level analysis. And here we transform from ICD space to DRG space by looking at how often the claims are coded by certain DRG frequencies. And we will say that the hospital is suspicious if they are using these DRGs more differently than their peers. Right? The peers here are hospitals that are that share similar characteristics. I will describe what we mean by peer. And this you can think of being local in rows. Right? So let me start with the first one. So this is global regression. So this is what economists call fixed effects regression. So the way we set up the regression is as follows. We are going to take beneficiary's medical history and code this in XI for patient or beneficiary I. So this reflects all the visits in the last 5 years to all the hospitals, all the codes and the DRGs that have been assigned, all the historical statistics, as well as their location, accounting for certain choices and location factors. And then we are going to throw in the hospital identifiers as also input features, right? So here, HJI variable is the count of visits by patient I to hospital J in 2017. And the coefficients here are betas, alphas, alpha J particularly, per hospital J, such that we regress all of this onto the total base payment or expenditure of beneficiary I in year 2017. Right? So we are trying to predict how much this patient is going to cost in the current year based on, and the hypothesis is that their past behavior and history, medical history, should be reflective of the spending in the current year. If it doesn't, anything will be showing up here as access. So what is this XI again? So it's the patient representation of the last 5 years. This involves all the past treatments in the form of ICD code counts, medical health, which we get from another database of chronic conditions for patients, as well as their location, so to account for their choice of what hospital they choose to go, as well as geographic differences in reimbursement rates. So if you look at the Y, which is the base claim amount, remember that we need to subtract all the factors from the total amount that are, additive factors like outlierness, disproportional, low-income patient share, and so on, just to look at the base payment amount. And here you're looking at the most expensive DRGs before we subtract the factors, external factors. So this is total amount distribution per DRG across hospitals or claims, and the base amount. So if you take out all the additive factors, we see the variance drops significantly. In fact, the variance ideally should be 0. The fact that it is not that much 0, although much smaller, is the fact that we are unable to take out all the additive factors, but much better than total. So the base amount is what we are going to be using in our regression. And the provided level fixed effect is exactly the alpha J, which this coefficient alpha J is the access cost simply due to visiting provider J over another provider. Right? In fact, alpha J is going to be our anomaly score, and it is directly explainable. It is in dollars, right? Because we're regressing dollars. And the explanation is that it is the average excess spending per patient visit at hospital J. Right? So this is a very intuitive explanation for the coefficient. And here are, based on our analysis, the distribution of alpha J coefficients that we have estimated from our data. I'll talk more about this. But one thing you notice is that a whole majority of them are above 0. Right? Very few are below 0, with access going as high as $60,000 per patient visit. Right? So the second approach is a subspace outlier detector. So here we're going to take all the hospitals and look at the count of ICD codes that they use in 2017. And there's a type here, this is provider representation. So this is a hospital by ICD code matrix, count matrix, right? And one thing we note is that ICDs can be substitutable. So some ICDs are really, can be used instead of one another. So to account for choices of which substitutable ICD codes are used by providers, we estimate some similarity between ICD codes, and our final provider representation is going to be a multiplication of the counts redistributed by substitutability. So this matrix is 7,600 hospitals by over 40,000 ICD codes matrix. Right? So this is very, very high dimensional, and not only detecting outliers in high dimensions due to density and distance becoming less relevant is problematic statistically, but also the fraudulent behavior is typically covered in the ICD coding behavior, right? They're not going to be manipulating all of these codes. So to that end, we're going to do some subspace outlier detection, and we will be using the state-of-the-art subspace outlier detections that I list here without going into the details. So here, the explanation can be in the form of which ICD codes are most proctored or manipulated by a given outlier hospital, which we can infer through some feature importance explanations through these detectors, such as the Shapley values. Lastly, we can look at a peer-based behavior discrepancy of hospitals. So the high-level goal here is to identify first related group of providers, right? Given a hospital, what other providers are similar to this provider, and find deviations from the group's expected behavior. Right? So this is the how far are you from her behavior. And the important question here is what makes two providers peers? What makes them similar? Because similarity is a philosophical concept. And here we use the definition of treating similar patient populations make hospitals similar, or using similar medical types of services that they provide makes two hospitals similar peers. So to that end, patient populations we capture through the chronic conditions database, and the types of services provided we capture by MVC frequencies. Right? So given the behavior profile of provider J, then we can define a distance between two providers. And here we are looking at the distribution of pairwise similarities among all these 7,600 pairs of hospitals in the US. And the peers of a hospital J is defined as all the providers with similarity above a certain threshold, which we use here as 0.8, which is the highest peak in the distribution. Okay. So here's how we find discrepancies in spending. So let us denote by VJ-DRG the frequency, DRG frequencies of provider J. Right? So this is a 740-dimensional vector of how often a hospital J uses DRGs in their claims. And let's assume the set of peers for hospital J is PJ. We take all the peer hospitals and look at their DRG distribution and take a weighted average. Right? So this is basically expected DRG frequency distribution based on providers J's peers. This is the expected behavior. Then we can translate it to a dollar amount in the form of an anomaly score. So what we'll do is look at the frequency for each DRG that the hospital J uses versus the expected frequency, subtract the two, and then multiply with the average base amount associated with DRG, right, which we call cost. So then this is if somebody is overusing a certain DRG or underusing a cheaper DRG, right, the costs will be positive or negative, and then we add over all the DRGs to see the total excess spending. So this also, anomaly score is also in dollars and also directly explainable to auditors in the form of excess spending over peers per claim. So this concludes the three different approaches to three different data modalities that we took. One thing to note here is that all of them are unsupervised, even though we set up a supervised regression here, there is no labels associated with fraudulency that we use. And they use different data modalities. Overall, we are going to be building an ensemble of these to do the final ranking of the hospital price suspiciousness. So let me share some results and we'll conclude. I will provide both quantitative and qualitative evaluation. Quantitative evaluation that I alluded to earlier, so we are going to go to the Department of Justice press releases. This is a website that looks like this, it's public, and we're going to use all of the press releases across years and search for the keyword Medicare. Right? So this gives us these public releases, and then we're going to scrape all of them, and these actually are DOJ cases that were filed for criminal cases, and they name hospitals using a partial name matching. We're going to isolate identifiers for hospitals, and those will constitute our set of known ground truth fraudulent hospitals. One thing to note here is that this ground truth is incomplete because, right, you detect what you detect, whatever you don't detect is unknown. So this is a form of positive unlabeled ground truth. So if anything, our detection rates will be a lower bound of the truth. So this means that we may be flagging a hospital that's not actually yet caught or against which a DOJ case was not yet filed, for example. So to that end, I will also provide some qualitative reasoning behind what we flag guided by the model explanations. All right? So quantitatively, when we combine all these 8 different anomaly scores from all the 3 different multimodal detectors using a ranking aggregation technique, we find that we can improve the precision at a current recall curve on average twice as better at detection rate at the top of the rank list than simple baselines. So here you're seeing in red our ensemble approach of precision versus recall, and the baselines in these colors. The baselines are very simple things like just looking at the total amount, most expensive hospital, based on total versus base payment amounts, and the dashed line is the random, right? If you just randomly sampled hospitals for auditing, you would just get 5% on average, let's say. And we're improving the precision twofold. And here when we look at targeting the top fraction of the rank list, as we go along from top to bottom, the lift, as opposed to random targeting, lift of random is at 1, and we are increasing an average of the lift by 4-fold. And if you look at only the top 50 hospitals, we actually find 21 in our top 50 of the name in the DOJ corpus, as compared to 1 in 20, 5% overall. This is an 8-fold lift at the top of the rank list, as compared to 4-fold lift on average across the rank list. And this is good because the auditors have only limited time to attain on to the top of the rank list. So we are going to go through some case studies just to give you an intuition of what we flag, is it meaningful, or how can we interpret the detected anomalies. And I would like to remark on every one of the detection methods and what they are explaining. So all of them are actually hinting towards some economic discrepancy. So the explanation is through sort of value, dollar amount. So the first global regression is actually directly reporting the fixed effect coefficient, the additional dollars that you will incur by just choosing that hospital. The second one is going to pinpoint to feature importances to certain ICDs that might have been manipulated by a provider. And we're going to relate each ICD to the DRG that it's most frequently used with, and DRG is associated with fixed amount, so that's how we're going to go from ICD to dollar. And lastly, the peer-based analysis, actually, the anomaly score itself is access spending, so directly again translates to the access dollars by a provider. So I'll share 2 case studies. So the first one is the top rank provider in our ensemble, which is Cleveland Clinic. So this is in the DOJ corpus, so this is in the ground truth. And I need to disclaim, right, that I'm not saying that Cleveland Clinic is fraudulent by any means, right, but there is reason to believe that they may incur, further scrutiny into their spending behavior through the analysis that I'll provide. And further, they have actually settled with DOJ in 2 different years for millions of dollars in the past. So that means that they have done some things in the past, although the reasons we detect them may be different than the reasons they were filed for DOJ cases. So the first model, the fixed effect regression, under this model alone, right, even though they're at the top rank in the ensemble, under this one model alone, they are ranked in the 27th position over here, right, top to bottom. And here the alpha J coefficient is nearly 30,000, which is 3 times the average. Right? So this is clearly some access spamming is going on. And the second model, the ICD subspace one, is giving us feature importances in the form of top 10 most important ICD codes. Most important meaning these are the ones that they stand out being anomalous. And when we look at the descriptions of these codes, they are often very ambiguous. So we see things like not elsewhere classified, unspecified, or other, and not elsewhere classified. So this implies that these ICD codes are used, under ambiguous situations. And some of which, if we relate the ICD codes to the DRGs to go to dollar amounts and look at the dollar distribution, we find that 6 out of 10 codes, top 10 codes, are with dollar amounts above 15 percentile, and 3 out of 10 is about 90th percentile. So these are statistically significantly overpriced ICD codes. Right? So finally, the peer-based analysis, we can look at the peer summary DRG frequency distribution versus the Cleveland Clinic distribution. And immediately we see some overuse of certain DRGs, right? So for example, DRGs 19 and 20, which are again cardiac valve and other major procedures, again points to some ambiguity, and some other overly used DRGs. Right. The second case study is the 5th rank position in our rank list. The reason I'm providing this is because the first 4 are in the ground truth, and I want to share with you something that's not in the ground truth. Yet we can use our explanations to make some sense of what is going on. So here, again, if you look at the top 10 most important ICD codes associated with this one, we see some ambiguously coded ICDs very often, such as other causes, external causes, and so on. And again, they are overusing ICD codes with high dollar value percentage. And with respect to the peer-based analysis, we are looking at the frequency distribution of DRG usages, and immediately we see again some overuse of certain DRGs. Right. So to wrap up, I will share with you our ongoing work and some future directions. So currently what we are trying to understand is to characterize the providers with large anomaly scores that we are detecting. So one question we can ask is there any pattern to the anomalies, right? Are they mainly from, I don't know, Florida? Are they mainly private hospitals? And so on and so forth. So this actually is a second level regression, if you will, from hospital characteristics onto the anomaly score that can highlight what type of patterns are there among the hospitals found to be fraudulent by our methods at least. The other thing we are doing is carrying this provider-level tools that we have designed to physician-level misconduct, right? So these are different entities, but at the end of the day, each one can be represented by a set of claims that they associate with, right? Providers have a set of claims that they submit every year. Each physician attends to a patient that ends up with a claim, so all of this can be generalized to physician-level fraud. And this need not actually be fraud only. So more recently, I'm collaborating with a University of Pitt investigator that is trying to identify physician-level systematically biased prescriptions in terms of contraceptives, right? So with certain state-level changes in the abortion system in the US, it becomes extremely important whether the physicians are sort of providing biased contraceptive prescriptions. So you can actually study their claims and find out whether there are systematic biases in the way they are handling their claims as opposed to, let's say, their peers. Finally, I've shown you results from a snapshot analysis. We are only studying 1 year while using some historical data to represent a patient. But there is no temporal behavior analysis that we have done yet. So this is a scale issue and time issue, but this is future work. And under the hood, everything is connected to everything else. What I have not actually told you is, right, you can think of this entire system of physicians working at different hospitals. And by the way, in the US, a physician can work at multiple hospitals or own multiple hospitals, own shares at multiple hospitals. And patients also going to different hospitals for various treatments. So under the hood, we can talk of a tripartite network and where a claim can be taught as a hyperedge and graph-based tools can be employed to detect and quantify fraud, which I'm also interested in due to my background in graph-based relational fraud detection in the past. Okay, with that, you can find a link to our paper if you want more details on this work at archive. And I thank all the supporters, starting with NIH and my collaborators. Thanks for your attention.
Thank you so much for your presentation, Professor. Is there some questions from the audience, please? Some questions?
I actually have one. It's mostly about the error and how can be impactful to find a false positive as well, and what is the borderline that you're going to see this is fraud, instead of...
Yeah, great question. This is the most frequent question that I get. What about false positives? Because a lot of practitioners are tired of anomaly detection tools due to the excessive number of false positives. And so what I've shown here is actually sort of, you can think of precision the opposite of false positive at a certain recall level. So at the top of the rank list, we're doing pretty well. And what is important here is that, what is the alternative? The alternative is that just random sampling. Like if you don't have any clue as to how to audit, the auditors are just going to randomly sample without introducing any other biases, right? That level is actually what we show here in the black dashed line. So on top of that, if we provide higher lift, meaning that the top of the rank is, the precision is higher, they actually have a higher hit rate going through the recommended hospitals for auditing. So the hit rate is increased here. It's not to say that false positive rate is 0, but that's why we need explanations. So this, I did not talk about neural networks today, right? Because everything needs to be explained, and further it needs to be explained in dollar value, because what auditors also care about is what is the impact, right? So at the end of the day, the government is willing to spend money on healthcare. How much of this is really big loss versus low loss? So this also kind of changes the priority as to which hospitals to audit, right? Rather than an obscure anomaly score, the dollar value dictates a good priority for them to attend to achieve bigger savings. So the explanations are very key to avoid this false positive issue and having a dialogue with the auditor.
Another question, please? Yeah, I have a question. I see that you use a shape technique to explain it. Did you use another algorithm like line, for instance? Is it possible to use this kind of algorithms?
Yeah, so line actually is has some known issues around how you choose the local vicinity for which you do a regression, and so we have not studied Lyme. I think there are better versions of it now in the form of even by the same author, I believe. But here what we needed was to really, because this is a subspace detection approach in the ICD space, our goal was to pinpoint specific ICDs so that the claims can be investigated as to, okay, are these the right ICDs to code the procedures and diagnoses as a starting point for the auditor. So any feature importance approach that can pinpoint these specific ICDs in the feature space is what we needed, and I think Shapley is expensive yet is a good approach that accounts for co-occurrences. So that's why we used Shapley in this case. We did not explore beyond that.
Okay, thank you so much.
It's another question about ICD, actually, because not every procedure is, or maybe I'm wrong, is listed in ICD. So how do you do when it's others? Because there are some categories in ICDs, others, for procedures or these kind of things. How you can explore specifically those cases, because they are going to be categorized like when you're creating your matrix, so it's going to be in a category like others, and these others may have a specificity. I mean, they have specific cases as well. How do you do there? Because it can be very wide.
So I guess you have more knowledge than I do about the healthcare system, payment system and ICD coding and so on. I have studied this 1 year just to learn the background data. We can talk more about how other things are coded, but my understanding is that there are ICD codes that are like catch-all, right? Other. So any kind of disease like knee, surgery or kidney transplant or whatever will have another category. And then those others are catch-all. If the coder doesn't know what has been prescribed or treated, doesn't fall under anything specific, they'll go this catch-all thing. And what we have seen is that the way other is used is suspicious among those pills that we tend to flag. That's why these ambiguous ICDs or catch-all ICDs are coming up more frequently. So yes, other exists, it's ambiguous, but some item providers are taking more advantage of the ambiguity than others. Right? So it's relative in that sense. I'm not sure about how exactly medical coders think about the other ICD codes.
Yeah, sure.
In more detail, we're probably more familiar.
Sure, thank you. Any other question? ¿Otra pregunta? Pueden hacer en español, la traducimos. Yeah. I can continue with making questions, but I think I'm going to stop there. Thank you very much, Lehman. Agradecemos a Lehman, por favor. Vamos a ir por el almuerzo, tenemos una pausa de 1 hora simplemente y la presentación que está para este momento la vamos a pasar después del almuerzo. So we don't have Hassan's talk after lunch. So we are resuming at 2:30. Estamos continuando a las 2:30 p.m. Con las otras exposiciones de los autores.